We're surrounded by gases, right? Air, for example. But you can't see them. So how do we even begin to wrap our heads around what they're doing? I mean, what's actually happening on a super tiny microscopic level that lets them, fill up a balloon or pump up a tire? Well, let's dive right in.
And really, that's the core question, isn't it? You can't see a single particle of gas, but their effects are all around us, every single day. Think about it. When you pump up your bike tire or just watch a balloon get bigger, you're seeing what trillions and trillions of these invisible little things are doing all together. So the real puzzle is, how do we connect what our eyes can see with this invisible world that's making it all happen?
Okay, so like any good mystery, let's start with the clues. These are the big things we can actually observe about any gas. First off, they don't have a fixed shape or size. You can't pour a gas into a bowl and have it stay there, right? Nope. It just takes the shape of whatever's holding it. Second, they'll expand to fill any room you give them, literally any available space. And maybe most importantly, they're always pushing outwards, creating what we call pressure. So these are the big picture behaviors we need to figure out.
Now, to crack this puzzle, we're going to need a special way of thinking. A tool, really, that helps us bridge the gap between our world, the macroscopic world of things we can see like pressure gauges and party balloons, and that hidden microscopic world of individual particles. And that amazing tool? It's what scientists call a model.
And here's the big one, the kinetic theory of gases. Now, the most important word here is model. This isn't reality itself. It's not a perfect photo of what's happening. Think of it more like a powerful, simplified story. A set of rules about this microscopic world that, if we follow them, should perfectly predict the behavior we see in our world.
So this is the magic trick right here. This theory is like a translator. It takes our everyday experiences and translates them into the language of physics. That pressure we feel from the air in a tire, the theory says, hey, that's not just some random force. That's the combined punch of countless molecules slamming into the tire wall. And temperature, what we feel as hot or cold, is really just a measure of how fast and energetic those little molecules are zipping around. This is it. This is the bridge connecting those two worlds.
All right, so for any good model, we need a main character. Let's design the star of our show, the ideal gas particle. We're going to build this thing from scratch, piece by piece, based on a few really simple but super powerful ideas. So let's get to it and design the perfect molecule for our theory.
Okay, rule number 1, its identity. We're going to assume that every single molecule of a gas, let's say oxygen, is an exact clone of every other oxygen molecule. We'll picture them as these tiny, perfect little spheres. They're also totally rigid. And here's the super important part. They are perfectly elastic. What does that mean? It means when they hit something, they bounce off with the exact same amount of energy they had before. Imagine a super ball that could bounce forever and never ever lose its bounce. That's our molecule.
Next up, we have to talk about scale, because this is a big one. The theory assumes these particles are almost unimaginably small, so small that their own size is basically zero compared to the massive amounts of empty space between them. Seriously, picture a couple grains of sand floating around inside a giant football stadium. That's the kind of emptiness we're dealing with here.
And check this number out. It really drives the point home. The molecules themselves, they only take up about 0.014% of the total space. Let that sink in. That means that more than 99.9% of what you think of as a gas is literally just nothing. Empty space. And this is a huge aha moment. It perfectly explains why gases are so easy to compress. You're not actually squishing the particles, you're just squeezing out all that empty space.
Okay, so what about their social life? How do these particles interact with each other? Well, here's the funny part. In our perfect little model, they don't. They're like the ultimate introverts. We assume there are absolutely no forces pulling them together or pushing them apart. They just fly right past each other without a second glance. We even assume gravity doesn't really affect them because they're so tiny and moving so incredibly fast.
All right, so we've got our perfect molecule. We know what it is. Now, what does it do? Let's lay out the rules of the game for how it moves around in its world.
Well, for an ideal gas molecule, life is just one big, chaotic pinball machine. They are in constant, random motion, flying off in every direction you can imagine. And they're not all moving at the same speed. Some are slow, some are crazy fast. But here's the key. They always travel in a perfectly straight line. Until, bam, they slam into another molecule or hit the wall of the container. So what happens in that bam moment? When they do collide, this is where that perfectly elastic rule we talked about is so crucial. In these collisions, zero energy is lost. None. The total energy of motion before the crash is the exact same as the total energy after. The molecules might just swap some energy and momentum, like billiard balls, and then fly off in totally new directions, but nothing is ever wasted.
So you can basically sum up a molecule's life like this. Long, lonely journeys in a straight line through tons of empty space, with these super quick, instantaneous collisions happening every now and then. The actual time they spend in a collision is practically nothing compared to all the time they spend flying around freely.
Okay, we've built our particle, we've set the rules for its world, now it's time for the payoff. How does this whole model, this idea of tiny little spheres just bouncing around like crazy, actually explain something real, like the pressure that's strong enough to hold up a car?
It all boils down to this one, simple, powerful idea. This is the absolute core of it all. Pressure isn't some weird, invisible force. It is the direct, physical result of our tiny molecules slamming into the walls of whatever is holding them over and over and over again.
Let's walk through it, step by step. 1. Our molecules are flying around at insane speeds. 2. They're constantly hitting the walls of the container. That's unavoidable. 3. Every single time a molecule hits that wall and bounces off, it transfers a tiny little bit of its momentum, a tiny little push. Now, one push is nothing, right? But what happens when you multiply that tiny push by billions and billions and billions of collisions happening every single second? Well, that massive, non-stop barrage of tiny pushes adds up to the steady, powerful force that we call pressure.
And there it is. That's the whole shebang. Just by making a few simple assumptions that gases are made of tiny, perfectly bouncy spheres that are always moving and don't interact, we can logically explain why they act the way they do, why they fill any space, and why they exert pressure. Now, it's really important to remember this whole framework describes an ideal gas. It's a perfect simplification, but it's an incredibly powerful one that gets us so close to understanding how real gases actually work.
So, that leaves us with one last question to chew on. This model, it works brilliantly for an ideal gas. But what about real gases? They aren't always so perfect. In the real world, molecules do have a little bit of size, and they do have tiny little attractions to each other. So, the real question becomes, what happens when those tiny imperfections actually start to make a difference? Well, that sounds like a story for another time.